I have the pleasure to introduce the speaker. So Professor David Snoke is a professor at the Department of Physics and Astronomy at the University of Pittsburgh. He received a bachelor's in physics from Cornell University and a PhD in physics from the University of Illinois at Urbana-Champaign, after which he was an Alexander von Humboldt postdoctoral fellow at the Max Planck Institute in Stuttgart, Germany, working with Manuel Cardona. After a brief stint in the aerospace industry, he joined the University of Pittsburgh in 1994. In 2006, he was named a Fellow of the American Physical Society for his theoretical and experimental work in optics and solid-state physics. He has authored or co-authored over 150 journal publications and has published 5 scientific books with Cambridge University Press and Pearson. And today he will be telling us about a possible path to room temperature superconductivity via charged excitonic complexes in 2-dimensional materials. So David, please.
Well, thank you. Are you recording this? Is this something that I could actually link to for people here?
I think Yisai is recording, is that correct?
I see it, it says it's recording. Okay, very
good. Yes, I'm recording.
Fantastic.
Okay, wonderful. Yeah, well, so this is something completely new. This is the first time I've given this talk anywhere, and I'm very happy to have you guys sort of be the first audience to see it, and I'd be very interested in your feedback on it. So I'm going to try a screen share. I think I have permission. Okay, you have to permit me to do screen sharing.
Yeah, Tim, give David co-host.
Yeah. Okay, now it says I should be able to. Yep.
Okay now, yeah.
Yep, okay, good. So I'll do that. And then I will go to the screen view here. Oops. All right, can everybody see that?
Yeah.
Yes,
Good.
okay.
Yeah.
All right. So this is something new in the last year. And as I said, this is the first time I've given this anywhere. So I'd be very interested in whether you think it's really legitimate or, you know, what you think of it. I find it fascinating and exciting and interesting. And I almost believe it myself now, since we've reproduced it about 3 times. So I'm starting to actually believe it. You know, they say a theorist is somebody who they believe their result and nobody else does. And an experimentalist, everybody else believes their result and they don't believe it, right? I kind of pretty much actually believe this at this point. So we'll see what you think. All right, so I'm going to, so just before I forget, my group, Zheng Sun is a postdoc. He will be moving to China actually in November. And John Beaumarriage is the senior graduate student on the project. And as many of you know who've worked with 2D materials, with exfoliation, it's a kind of painstaking to, you know, peel off these little layers and lay them down on top of each other and so on. And then at the end, you just present it and it looks beautiful. And you don't have to actually think about all the pain that was gone through to make all these samples. All right, and the theory is all from Igor Bondarev, who have had a really nice collaboration with in the past year. Okay, so I'm going to start with a very general introduction about superconductors. And this goes all the way back to the 1950s, when this was really the hot topic of physics at the time, at least in condensed matter physics. Really exciting times. And people had experimentally seen liquid helium. And they had experimentally seen superconductors, low temperature superconductors. And London had just come up with the theory, you know, sort of in the 40s for liquid helium as a Bose condensate. And that was very exciting and it worked pretty well. And, you know, there sort of was a natural question in people's minds, you know, how do we understand superconductors? Is this related? You know, how do we understand it? And the first note really talking about this was by Schafroth in 1954. And in those days, Physical Review had letters that were literally just letters. And this was a 2-page informal letter that was written by Schafroth, but he really laid out a lot of things that became part of BCS superconductivity. So in his short letter, he proposed a pairing mechanism for electrons, but he did not have the polaron pairing mechanism. And that, of course, was due to Cooper, who eventually came up with that mechanism. And Schafroth also correctly noted that if you had a set of Cooper, well, they weren't called Cooper pairs at the time, you had a set of pairs of electrons, they would be bosons, and then they would undergo Bose condensation with a well-defined TC, and this might, in fact, be then the explanation of superconductivity, because they would be a superfluid, and a superfluid would show the behavior that was seen in the superconductors that were going on. And so this is what's called Schafroth superconductivity. And basically, it's a correct theory that if you take a normal BEC Bose condensate of charged bosons, it will not only be a BEC, it'll be a superfluid, and the superfluid, therefore, will have superconducting properties. So the time scales, were moving really fast in those days. So in 1957 is the famous Bardeen-Cooper-Schreiffer paper, which lays out all of the elements for what we now call BCS superconductivity, which is the main one that we actually understand. And of course, all the elements that we now think of as standard BCS theory were all there. So first of all, Cooper pairing based on the polaron effect. And so let's see here. I think I can make my pointer become a laser pointer. Okay, so you can all see that there, right? So this is your basic Cooper pairing mechanism, that each electron has a little bit of self-trapping going on due to the polarization of the lattice. And you have to have polarizable optical phonons in the lattice for this to happen. Each one makes a little dimple, and then that leads to a net force between the two, and you get Cooper pairing. And this is sort of the standard picture that's usually presented, two people sitting on a couch, making a dent in the couch, and it sucks them together to make them sit in one dent. The theory, so it turns out in actual BCS superconductors, the TC that we see is the TC for becoming pairs. So from going from free electrons that are unpaired to a pairing up. And so the TC is related to the binding energy of the pairs. It's not the BEC critical temperature, which is actually much higher. And in the context of high TC, there's been actually debate about whether it could be the other way around. So you could actually, these are two different TCs. And so if the condensate TC is much higher than the pairing TC, then as soon as you get to pairs, you're also automatically a BEC. But it doesn't have to be that way. And so some people have proposed with some superconductors that you first have pairing at high temperature, and then you have to drop the temperature below a lower TC before you actually get BEC. And that's still a controversy. They call that a preformed pairs threshold. And that's still somewhat a topic of debate for high TCs. The other thing that happens in a BCS superconductor is that there's a high density of electrons, and so you have a Fermi level. But it is still the case that there is a condensate of bound electron pairs. The essential physics is that you have a condensate of pairs, and I'll talk about BEC, BCS crossover in just a second. And the famous energy gap that opens up with BCS superconductors is it really just a vestige of the pair binding energy. So you have the picture of two electrons with a binding energy, and then to break those apart, you get two free electrons, and you have to pay the binding energy cost for that. Okay, so interestingly, oops, I see I have some uncontrolled things here. I was at Illinois when Bardeen was still alive, and chatted with him a few times. And it's quite interesting, actually, the history of this. He was absolutely insistent that his BCS theory had absolutely nothing to do with BEC. And so up through the early 90s, you would have physicists who would be adamant that BCS has nothing whatsoever to happen with BEC. And, you know, to be a little cynical, some people would say, well, Bardeen didn't want to share any credit with Schafroth to have anybody think that he was just sort of, you know, second fiddle to somebody else's theory, you know, and, you know, in his mind, they had a completely original theory for which, of course, they got the Nobel Prize. However, as early as 1964, J.M. Blatt comes out with a book, Theory of Superconductivity, and shows that the BCS wave function is identical to a BEC wave function. They are both coherent states. And in my book, I have a book some of you may have seen, Solid State Physics. In the last chapter, I talk about the theory of superconductivity, and I review Blatt's theory, in which you basically can see that the BCS wave function can just be simply rewritten as a coherent state of pairs, and you get all the same thing. And so, in general, the field of BEC to BCS crossover has been an active field. So Blatt, again, you know, politically, he was on the outs. He was sort of a minor character compared to Bardeen. And so there was people who were just adamant that this was nonsense and that BCS had nothing whatsoever to do with BEC. In the 80s, moving forward a little bit, BEC-BCS crossover became popular again, in which Keldysh and Nozier and co-authors of theirs had a series of papers in which they looked at the crossover from BEC to BCS. And in the case of excitons, there's a pairing mechanism in which it's a Coulomb attraction between the electron and the hole. So it's not a Cooper pairing, it's a negative particle and a positive particle attracting each other. You can go through the same crossover between BEC and BCS. So here's a picture that's actually from Keldysh's, one of Keldysh's papers, in which this is the occupation of the electrons as a function of K. And in this limit, you're in the BEC limit. And this is just the Fourier transform of the pair wave function of the, you know, so you would just have a hydrogenic Rydberg wave function in real space. And if you Fourier transform that into K space, you would just have this wave function here. And then if you increase the number of excitons, you just keep the exact same shape and just amplify it up, just make it higher. And so that would be the BEC paired paired.
You don't need
Is there a question? I'm happy to take questions in the middle of the talk if people want to jump in there. Was there a question? Okay. Feel free to flag me for questions. Okay, so in the BEC limit, we just raise this up, but you can see there's an intrinsic problem, which is you can't have an occupation of the electrons greater than 1 because of the Pauli exclusion principle. And so if you keep raising the density, eventually you hit the maximum, and then the pair wave function has to be renormalized. And so the pair wave function, instead of just being the hydrogen Bohr atom version, it starts to look like a Fermi level. Okay, so you see a flat region here and then a crossover. And so this is the BCS pair wave function. And it looks a lot like a Fermi C, but it's not. It's actually a coherent state of bosons or of electron pairs. And this is the pair wave function which they're in, which has, of course, been renormalized very strongly due to the Fermi, you know, the Pauli exclusion of all the other ones. Okay, so this was all worked out in the 80s in the context of excitons. And since the excitons don't conduct charge, that is insulating a neutral state, and that's called an excitonic insulator, or EI. And so ever since then, there's been a number of experimental claims to have seen this excitonic insulator state in various systems, and I'm not going to talk about that in any great length. Well, since the 90s, with the discovery of cold atom BEC, people have done lots of theory and experiments where you can simply tune the interaction strength and go continuously from the BEC to the BCS limit. Randaria was one of the first people to really do this theory. And again, just to tell you about the nature of the times, he has a lengthy review article in our book from 1995 that Alan Griffin and I published on Bose condensation. And it was actually controversial whether or not to include his article in that book, because it was still at that time considered to be very radical to say that BCS had anything whatsoever to do with BEC. And yet now it's a standard theory. And you can simply tune the interaction strength. And you can see you can go either at high temperature from unpaired fermions to uncorrelated pairs, or you can at low temperature have what basically looks like a BCS theory, or you can just move continuously into a BEC. Okay, so that's all the history of BCS. The problem that we all know is it's hard to get a room temperature BCS superconductor. And that's because the Cooper pairing mechanism uses a phonon as an effective boson to mediate the interaction. And that typically that strength of that interaction is going to be a fraction of the phonon energy. So if we have a optical phonon typically in a solid of 30 to 40 millivolts, this is going to give TC, you know, of say 3 to 4 millivolts. And so it's going to be very hard to get high temperatures of BCS superconductors. Now, the high TC superconductors are still debate about the mechanism that's going on, but most people believe there's some kind of bosonic quasi-particle, probably not a phonon, although there are people who also argue for phonons as the mechanism for pairing for high TC. But in any case, you have some kind of bosonic quasi-particle that's playing a mediating role and making something like Cooper pairs happen, as in BCS. And, you know, after, you know, I was at the Woodstock of physics in the late 80s when they announced the high TC result, and I've never before or since seen a mob of physicists go crazy, but that was what was going on there. Ever since then, though, we've not really been able to raise the temperature by a whole lot more to get it up to room temperature, although it's been a very active field of research. Okay, so now here's where we start to focus in on the experiments that we've actually tried to do. This is a paper that I remember seeing back in the 90s. Vladimir Yudson from the Lozovic group, he had moved to Israel at that point, proposed a way of making charged bosons using an excitonic mechanism instead of any kind of Cooper pairing mechanism. And the idea of this is basically, just as we can have tryons in semiconductors where you have, say, 2 electrons in one hole, you can just go one more and have a quaternion. In which case you have, say, 3 electrons in a hole, or you could do it with p doping and have 3 holes and 1 electron. In that case, you have a boson because it's 4 fermions, but it's charged. It carries a net charge. And so if you made a condensate of these, it would be a Schafroth superconductor. I thought that was a really neat idea at the time. I remember seeing it. But the problem was that the system he proposed it in was gallium arsenide quantum wells, and I think I talk about it here. Let's see. He proposed it for semiconductor quantum wells, and the binding energies of those typically were like 10 millivolts, and the line widths of the excitons were, you know, of the order of 5 to 10 millivolts, and so the possibility of actually distinguishing these states from each other looked just really not promising, although people were able to see tryons in the early 2000s looking at 3.5 semiconductor quantum wells. So I want to emphasize here what's going on is that this is a binding mechanism that is just from Coulomb attraction. And so it would be essentially exactly analogous to a doubly charged hydrogen atom, right? So you start with a hydrogen atom and add 2 electrons. And people have actually done that calculation. And you find that it's metastable for hydrogen. It is, even in hydrogen, it's not impossible to get that, but it has a higher energy than the molecular hydrogen or just the hydrogen by itself. So it'll tend to only be metastable. But what got me interested last year is just thinking about now with these 2D materials, the scale of the energies is now completely different compared to what we had back in the 90s when Yudson made his proposal. So typical exciton binding energies are, 100 millivolts up to half an electron volt. And so the quaternion binding energy, you expect to be some fraction of the exciton binding energy. And so it's not really standing on your head to get quaternion binding energies that are already up at 25 millivolts or more and become therefore feasible at room temperature. Now there's some other room temperature issues that we can talk about. But in general, one of the reasons for this is just because these 2D layers are surrounded by low dielectric on either side. And so the binding of the electron hole in general is much, much stronger. How do we get these things? And that's going to be basically the next section here. Okay, how do we get, it looks like it shouldn't be stable, right? We've got 3 like charges repelling each other and only 1 positive charge. Like, how could this thing possibly be stable? It's not, there's, it's not a Cooper pairing at all. It's just literally finding a bound state of these particles. All right, so here's the trick that Yudson proposed. And it is to make a bilayer system next to a metal. All right, so this is the real system up here, okay, consisting of, this is Yudson's proposal. So you have a doped layer, which has some excess charge, and then you optically excite it so you get an exciton, and the exciton is then bound to 2 extra charges. But what makes this thing stable, and this is really the nice idea that he had, is the fact that if you put it next to a metal, and it's a good metal, you have image charge here. So this looks like then the following complex, which would have 8 charges, because the image charge in the metal gives you 3 positive charges and 1 negative. And these positive charges act to cancel out the repulsion of these negative ones. So you have, in general, the screening in the metal will screen out a lot of the repulsion, but still leave enough attraction for these things to be stable. Over the past year then, Igor Bondarev has been doing calculations, and the first thing he noticed was that actually there's a lower energy configuration than the one that Yudson proposed. So actually the lower energy configuration is to have basically a trion in one layer and then a extra free charge in the other layer. And so trions are already well established to happen in these 2D materials. Again, you make a dope layer, you optically excite, you get a trion, and now you pick up another charge in this other layer. And once again, the metal plays the role of creating image charge that then cancels out a lot of the repulsions. And of course, the other thing that's going on is because of the bilayer, some of this charge is pushed away so that, the repulsion of this electron to that electron is pretty weak because it's been, it's far away. Okay, so this is what we want to try to look for. So Bondarev did the calculation, and there's 2 parameters here. Keep in mind, there's the distance L, which is the distance between the 2 layers. So this is a 2D material, this is a 2D material. And then there's the distance D to the metal. So this becomes like 2 parameters that you can vary and see how this affects what you're predicting. Notice that the recombination in this would basically be sort of a renormalized indirect exciton. You'd have to have recombination between a hole and an electron between the two layers, so that would be spatially indirect. Whereas the recombination here, well, it could be indirect, but you have a much more probable recombination of a trion, basically an electron and a hole meeting in the same layer, which has a much larger oscillator strength. And so this becomes the dominant decay mechanism for these guys. Again, stop me with questions at any point. Okay, so the theory that Bondarev did with collaborators is actually well established. He started with his calculation for trions, which he did, that was used to actually give predictions for data that the Philip Kim group did, in which they saw fairly believable trion signals, and then simply adding the extra charge here to get a quaternion. And so he's able to adapt an existing theory that was fairly sophisticated and show that this thing is then stable. So I'm not going to go through all the gory details of his theory. I'll just say a few things. So first of all, question? I'm hearing voices. I can't tell if someone's trying to ask a question or if it's just background noise here.
It's probably just accidental.
Yeah, probably people should mute themselves if they're not asking a question.
I think it's just when people join, they don't yet have the microphone muted. So sorry for that.
Okay. Wonders of technology. All right, so basically, if we think about a trion near a metal, you have sort of the original terms of the attractions and repulsions of the various particles. And then you have these extra terms for the repulsion and attraction from the image charge. And then when you add the fourth particle for the quaternion, similarly, then you have all these terms of all the different possible just geometric potential energies for all these possible charges attracting and repelling each other. And so you have to add all that up. And that becomes a potential energy. One little complication that you have to pay attention to is you have to think about what we're doing here. We're looking at a photon coming out. We're going to do spectroscopy, so we're going to optically pump, and then we're going to just look at the luminescence spectrum coming out. And so in the case of an exciton, when the exciton recombines, there's nothing left. And so you have just the energy originally of the exciton is the energy of the photon. In the case of a trion, your energy is the initial energy minus the final energy, and the final energy is one free carrier and its image charge, because that free carrier is still sitting next to the metal. And for a quaternion, the final state is 2 free carriers and 2 free image charges. So the photon coming out is equal to this difference between the initial total energy and this final energy. So we have to subtract these off to be consistent. So I'm just going to jump to the conclusions of the theory here. And it's actually quite nice. Basically, the result is that you don't have to stand on your head to have just exactly the right parameters, that you can get a stable quaternion for a really fairly wide range of parameters. So if you look at this figure here, okay, this is D, this is the distance to the metal, and this is the layer, this is the 2 monolayers, the spacing between them, okay? And then you can see the quaternion recombination energy is this sheet here, and the trion is here. And so for a wide range of energies, the quaternion sits above the trion in its photoemission energy and below the exciton energy. And so now you see here just a slice where we've picked a specific L, and now we're putting actual units on this. And you can see that, these are very, it's a very stable system. We don't have to get precisely the right D or precisely the right L in order to have the quaternion be stable. It actually then, as I'll show you in the experimental data in a minute, the ordering of the lines, where the quaternion sits, and the actual energies turn out to come out in agreement with the experiment. Basically the main parameter which is being varied is the screening parameter in the Coulomb interaction. So you have a sort of a screened Coulomb that you have to take into account, and that becomes essentially a fit parameter because we don't know that from first principles. But the same parameter has to be used for the trion, the quaternion, the exciton, and so on and so forth. All right, so let's go to thinking about the experiments. All right, so this is the experiment then. This is
sorry, I think Justin has a question. Although
okay, go ahead.
I'm not sure exactly what he did. Well, he raised his hand somehow.
Hi, I'm Justin. I have a quick question. Probably something you already addressed that I didn't really quite understand. So the question is the following. So it seems to me that you're thinking of these quaternions, which seem like, you know, high order kind of complexes, high order excitonic type of complexes. And right. The idea was that you were thinking of trying to get a BEC of these charged bosonic systems. So why do you have to go to such lengths to get to look at the quaternions? Why can't you just use the trion, for example, to look for a BEC of the trion?
Well, the trion is a fermion, okay, and so it wouldn't make a BEC. On the other hand, you could think of something that might happen analogous to helium-3. So in helium-3, that's also a fermion, but you can get Cooper pairing of helium-3 atoms, in which case you have something like a BCS type state. And so you have to count up how many fermions that is, right? So that's six protons and 6 electrons making up a fermionic Cooper pair for helium-3. So one could imagine making a trion condensate going to low temperature and hoping to see something analogous to Cooper pairing in that case. I think that would actually be harder to do because it typically is a high density effect. One typically needs to see Cooper pairing of helium-3, you know, that's a liquid. So it would be interesting to do to look at what would be the TC predicted for Cooper pairs of trions, and that potentially could also be a candidate for a BEC as well. Now,
so your main claim is that the quaternion is the lowest charged boson in such a system?
It's the lowest charged boson, that's right.
Okay, great.
Mm-hmm. Other questions?
Actually, yes. Can I ask, related to Justin's question? So the trion is a fermion, but if you account for the image charges, wouldn't it become a boson?
You know, I thought about that, and I think the answer is no, because the image charge really is just a way of accounting for the screening. So if I put a single electron in a quantum well next to a metal, that electron will not act like a boson. Okay, and so I think the answer to that is that the screening charge is playing a role in the charge accounting, but it's actually not changing the statistics. It's not an actual fermion.
I see.
I'm pretty sure of that.
But okay, so then if you count the image charges for the charge, doesn't it mean the total charge of the quaternion is neutral?
Yes, except that you can connect a circuit just to the top layer, right?
I see. Okay.
I don't have to put leads to my metal and collect the image charge, right? So I can put an in-plane electric field in my real space, you know, where the quaternions live, and move them with an electric field that's in plane, and they will move in response to an electric field.
Okay, but then wouldn't you get charge buildup at one end in the metal?
Well, you have to complete. Well, you have no, because the image charge isn't conserved, right? If I take out, so I have to complete the circuit in the upper layer, and have, you know, when the quaternion hits the end, I have to do something like pair breaking to convert it into normal charge that leaves the system. But when that happens, image charge just vanishes, right? I mean, image charge is just an image. It's not real charge that's going to accumulate. So if I suck out the real charge, the image charge just goes away.
Okay, thank you.
Yeah.
Hey, David.
Mm-hmm.
I have a question here. So, you know, in order to have this, create this image charge, you want to put for example, the tungsten diselenide directly in contact with your metal. But on the other hand side, we know that those metal contact will dramatically change the lifetime of the photo-excited carriers, for example, excitons, right?
You're saying the contacts on the sides or the metal that they're sitting on top of?
The metal they are sitting on top.
Yes. Well, it will change the binding energy, which will change the oscillator strength. Yes. So it's not a super dramatic effect on the exciton, but it's a measurable effect on both the trion and the exciton.
Yes.
But it doesn't. It shifts them. So I mean, their binding energy of the exciton is like 80 to 100 millivolts. And the shift of the exciton is neutral, remember, so it's not strongly changed by image charge because it's just a neutral image charge interacting with the neutral exciton. That is shifted by maybe 5 to 10 millivolts, and the trion is shifted like maybe 10 to 15. So there is an effect. It's not a huge effect.
Okay.
It makes a huge difference, by the way, though, that we have HBN encapsulating everything. So if you look at this picture here, it's metal HBN monolayer, HBN monolayer, HBN. This is why I said it was a real project, you know, 7 stacks high, you know, or 7 layers high for the lab members. You certainly don't want the metal pushed right up next to the monolayer. That will do bad things, right? So the HBN between the metal and the first monolayer is an important part of this. You don't want current flowing in the vertical direction. Other questions or comments?
Oh, actually, I see someone else has the hand raised.
Yeah, I can't see that.
Yeah, thank you, Phil. Thank you. And I have a naive question. Actually, I understand that this kind of quaternion is one of the simplest complex of bosonic complex in this bilayer system. But what happens, is there a simple way to see that it can have a lower energy than the trion? And what happens to other configurations, like we have one exciton on each of the layer, something like that? Or even more complex system?
Yeah, so in general, there's probably going to be coexistence of all of these species. They're going to actually be, especially at room temperature, they're going to be close in energy to each other. I'll talk about at the end how we can sort of select out just one out of the bunch. But in general, there will be some kind of coexistence mass action equation that would, you know, give you a relative population of all three.
I see. Thanks.
And other things like biexcitons as well. Okay, so let me just run through the experiments. Metal, okay, HBN insulator, then the tungsten diselenide, another HBN, another monolayer, this one doped, p-doped, and then a top capping layer of HBN, all right? And here you can see an actual photograph in which all these layers were stacked up. We did not put contacts on any of this yet. We're just doing spectroscopy, although we've started to work on trying to put an in-plane electric field on these things, but I don't have anything to report from that. I have to say that apart from the nice oscillator strength and binding energy that you have for these monolayers, the fact that we have HBN to make a really good insulator is also a really important part of this because you don't want a lot of tunneling and a lot of current in the vertical direction. You want these things to be well separated. And that was always a problem with the gallium arsenide, was that if you tried to make this complex in gallium arsenide, the barrier height is not so high, you always end up with tunneling through that barrier. Okay, so here's some data. And this is in a variable temperature cryostat. Starting at low temperature, we just pump non-resonantly and then shift, just increase the temperature while keeping the laser power the same. And several different features here. Okay, so the nice thing in general, I would say, is these monolayers and tungsten diselenide in particular are well studied. So like every line is pretty much known in the literature. You can go and see, and just look up exactly what you got. And of course, the other thing you do, which we did, is you can make monolayers of this material. And anything that exists in just a monolayer, you're going to see just by itself. Okay, so here you see the exciton line. And that's exactly where it should be. And there's a band gap shift. Okay, so that shifts down to the red. Okay, that's called the Varshny equation. And also, as you can see, as temperature rises, there's a broadening, a line broadening due to phonon interactions. Now, you also have, this is a doped system, remember, and it's p-doped. We have a set of impurity lines, and the range of these impurity lines is also very well established in these things. And so what we see is those saturate both as you increase temperature and as you increase the density. So there's only a finite number of impurities. As you raise the temperature, all of the carriers pop off of the impurities, right? And if you raise the density, there's only so many impurities around, and so things are going to saturate that way as well. So we can see that, to me, is a really nice feature here. If you look in this middle range here, we've got three very distinct peaks, right? We've got the exciton, we've got the tryon, which appear in monolayers, and doped monolayers. And then in addition, we've got this new peak, all right, which appears in our structure. And we label that Q, and that's our quaternion candidate. And just to make a long story short, that is exactly where the Bondar theory predicts it to be. Now, to be fair, he has parameters he can tweak, but basically his tweaking affects both the tryon energy and the quaternion energy. So if he changes that parameter, both of these lines move. And so since we already know where the tryon is, we don't have a lot of wiggle room of where the quaternion can go, because you have to fit the tryon, and we know what that is because we see it in the monolayers without any bilayer stuff going on. All right, so we've reproduced this in 3 samples. Let me see here. Okay, yeah, okay, so that's just saying that's the quaternion line. Okay. And then we have identified all these other lines, and we've done a whole bunch of different control samples. I'm not going to show you all the control data. I will, I have some of that. If there's interest, we can look at some of that. So what do we see? We see in our various samples, we've got the exciton well-established, impurities well-established, tryons well-established. The biexciton is a strong function of pump power because you have to have 2 excitons finding each other. And so the biexciton only appears at high pump power. And the interlayer exciton appears way down here. And this little bump might actually be a vestige of that. And that is well separated in energy. It has a very different lifetime. It's a very long lifetime because there has to be tunneling between the 2 layers for it to emit. And so it's easy to identify. And so essentially you say, all right, the overall strategy, you say, okay, we'll first look at monolayers and see what we see there. We make the bilayer and say, what's new? Okay, there's only 2 new things. One is the indirect exciton that we already know all about, and the other is this Q line. All right, so, and like I said, unfortunately, at high temperature, they all sort of smear in, although you can see there's still sort of a double bump structure going on there. All right, so here's sort of a summary of many experiments, many structures that were made. Okay, so we reproduced this 3 times with 3 different samples. We did control samples. For instance, we made the bilayer without the metal. So everything exactly the same, but not the metal. We never see the Q line in that case, although we see the trion line. We never see the Q line in any monolayer sample. And if we make an undoped bilayer with a metal, we don't see it, okay? Nor do we see the trion in that case, because both of these need to pick up extra charge in order to exist. So without doping, you don't expect to see either of those. So the control samples all work as expected. As I said, the energies agree with the theoretical predictions, given the fact that we have a 1 parameter that we can vary but we have to fit both lines with that essentially 1 parameter. We also can just turn up the power. So sitting at low temperature, so this, I'm going to try to move this. This is kind of annoying here. I guess I can't move this while I'm in screen display. I can't see part of my screen because people's images are in front of it. Okay, so first of all, reasonableness says it's not some impurity, because impurities don't just magically appear in bilayers that aren't there in monolayers. And it's not an indirect exciton, because we know where those are. Okay, and a third evidence is that the impurity lines, a typical way to tell the difference between impurity lines and excitonic lines, is the fact that the impurities saturate because, again, there's only so many of them. And so if you turn up the pump power, you will overwhelm them. But the trion and the Q line basically are excitonic in nature, and so they scale linearly with basically with the exciton population. So at high power, you can see now that the quaternion, the exciton, and the trion are outweighing the impurity luminescence. So the quaternion line is not an impurity line, or I'll call it the Q line. You be the judge whether you think it's the quaternion line, but it's not an impurity line, and it's not an indirect exciton. Okay, why is the indirect exciton shifted so far away in energy? Okay, so this is a different set of data. So this is a bilayer sample with no metal. Okay, so first of all, in all these bilayer samples, when I have a doped and an undoped junction, in equilibrium, then there's going to be a band offset because the Fermi levels line up. And so you end up with then the indirect, spatially indirect emission is going to have much lower energy. And that's been well documented in a number of papers showing the indirect exciton. It's way down here in energy. And there's other things that really easily identify the indirect exciton. Like I said, it has much longer lifetime. So we do time resolved measurements of the street camera, and you see that it has a very long lifetime. And the other is that it's hypersensitive to the thickness of the barrier. So remember I said the quaternion binding energy is not especially sensitive to that thickness because it's just the Coulomb distance. But the tunneling rate for recombination through that is very, very sensitive, exponentially sensitive to that barrier thickness. And so if the barrier is too thick, you see no indirect exciton. So you only see the indirect exciton when you have a fairly thin barrier between those 2 layers. And in this particular data set, the pumping power was fairly high. So we actually see the biexciton appearing exactly where Tony Heinz's group saw it. This is a intra-layer. This is not an indirect biexciton. This is in a single, it's within one monolayer. It just happens that in this set of data, we were pumping with enough power that we could see significant biexciton emission. Okay, so in the last few minutes here, let me just talk about sort of where do we go with this. So first of all, like I said, I'm pretty much, seeing a line confirmed in 3 separate samples made by 3 separate students is making me a believer that is not just some random thing going on. under different conditions. So we could confirm it in a number of different ways. We could try doing it with a totally different TMD instead of tungsten diselenide. There's no magical reason why we picked that one other than we just had some good stuff. In particular, we had doped samples. A great experiment to do, which is a very difficult one, would be to apply in-plane field and look at the luminescence to see whether it actually moves in response to an in-plane electric field. So you have a signature of where these things are, and they move. We have done initial trials on this just to look at the diffusion in the plane, and they don't diffuse very much at all. They have terrible diffusion, and that's pretty well agreed upon. A lot of people have concluded that. I'll have some comments to make about that. So, step one is, do we really convince ourselves to really even have this complex? I think it would be extremely exciting to say that we can make charged bosons, even not knowing yet exactly what we can do with them. And so I think I would like to see confirming experiments, but I'm very convinced at this point. There's a bunch of theory questions. I talked before about coexistence with other complexes. There's a trick that we can escape that possibly. I'll talk about in a second. In general, the theory of a Schafroth superconductor is not worked out in anywhere near the detail that BCS is, because no one's ever seen one. But in general, you've got long-range repulsive interactions between all the particles. And that is going to lead to some renormalization of the properties of the BEC. And so the theory of a simply charged BEC with long-range interactions is not well worked out in the literature. So that's a very basic theory project. Maybe it doesn't make much difference at all. Maybe it does. This is also a steady state. We either pump it with light or with electrical injection, but either way, it's going to be a steady state type system. And so a lot of the theory that's been worked out for excitons and polaritons would apply in this case as well. Now, let me just say in general, making a pure excitonic BEC is problematic. So when the theory for excitonic BEC came out, it was actually proposed in the 60s by two people, Blatt and Moskalenko, independently. Ever since, there's been experiments claiming BEC of just excitons, and a lot of people aren't convinced of them. And there's an intrinsic problem in all these experiments, which is, in general, if you're looking at quantum wells or any of these things, you've got disorder. And to get BEC, you go to low temperature, and you've got a tight, small, tightly bound exciton. They're going to fall into local minima. And so you're going to have more like a Bose glass type state than a Bose condensate, where you may have like a bunch of independent trapped condensates. So none of the experiments that have been claimed out there for Bose condensation of excitons have shown the simple effect of interference fringes, of showing that you can get coherence, or the simple effect of line narrowing, never been seen for exciton condensates. Well, what was the trick that we all did? Okay, it was to make polaritons. And so why not apply the same trick here? So basically, you can make a polariton with any optical transition, anything that light will interact with. And so if we take this whole thing and put it inside a cavity, we can make quaternion polaritons. How's that for a complication, right? This is just sort of standard polariton theory to remind you. I know I'm speaking to an audience that's very familiar with polariton physics. If I have, say, two mirrors, and I have a confined state in there that's resonant with an exciton state, then I get an anti-crossing, and this becomes our lower and our upper polaritons. And so I could simply tune that to the quaternion transition instead of the exciton transition. Many nice things happen. You get line narrowing, you get a light effective mass, you get averaging over disorder. Just in a sort of hand-waving way, in general, the effective mass of the polariton is given by the cavity mass of the photon, not by the exciton mass. And so these masses are, 3 or 4 orders of magnitude lighter than an exciton. And so that means they're delocalized over a much wider range. And so they're averaging over that disorder. And so you see just very sharp lines for the polaritons that you would not see for the excitons in that same structure. The light mass also means that they have a much better diffusion constant, because the diffusion constant depends on the mass. This is already being used. People are making polaritons with organics, with excitons and organics to enhance the diffusion in organics. And that is like becoming a cottage industry in the chemistry field, because organics usually have terrible transport via diffusion of excitons, but the polariton can really enhance the diffusion. I'm going to skip this for the sake of time. So here's what I've hinted at before. Actually, there's another nice feature, which is I can tune the photon resonance to the quaternion resonance and actually favor condensation just for that one and leave the trine and the exciton behind, because they're not going to be resonant because they're at different energies for their photon emission. And so I could basically make a BEC just of the quaternion polaritons, which will have light mass, and the trine and the exciton will have heavy mass and won't even be condensates. And so that makes it nice. And this is just old data, very old data from 2007, showing exciton polariton BEC is now routine. We just go in the lab and turn it on these days and make condensates doing all kinds of fun things. So, this is kind of the thought experiment. One nice thing, lots of things are difficult here, but one nice thing is that the metal can also be a mirror. You can have a nice thick metal that is one of your mirrors for your cavity, and that should actually work for this scheme. So the idea is then you contact the monolayers in between two mirrors, you illuminate it, and now you've got a superconductor that's only there when the light is on. But potentially you can do it at room temperature, pattern this and make squids, and so on and so forth. One can always dream, but one has to walk before one can run. All right, so I'll finish since I'm almost out of time here. So strong points are the following. It's totally very, the theory says these things should be stable, and so it's not a reach at all to make these things. So making a condensate may be another story, but making quaternions is not some kind of flaky physics. It's actually, I was just surprised. The theory says they should be there all over the place, because they're stable and even robust for a lot of change of the parameters. If we can convince everybody that we've really seen them, this would be the first non-Cooper pairing mechanism for charged bosons in any material. And I think that's pretty exciting. The experiments agree with the theory, and we've done a lot of control experiments, every possible monolayer, bilayer variation of these things, and it's all consistent. And then basically that's where we're at, and one can dream about what one could do if you could actually get this to condense, and so on and so forth. But I'd be happy if I could be the first one to show that we have a non-Cooper paired charged boson. So with that, I'll finish, and I'd be happy to take questions. And definitely, like I said, this is very new, so probably a lot of things I haven't thought of yet. Thank you.
So unfortunately, we don't have an applause button, but I'm sure everyone is applauding behind the microphones. So thanks for sharing this very nice new idea and the very promising results. Let's see if anyone has any questions.
Yeah. I have a question. Hi, Professor. Yeah. So I have a question. Why you choose the tungsten dicellulite for this kind of experiment? You know, from my understanding, the tungsten-based material has a very complicated electrolytic, system. Optically, you can see very complex optical spectrum, which is, I think it's, your labeling is kind of oversimplified, I think. If you put two tungsten monolayer together, you can have, many possibilities, I think. Okay. Yeah.
Well, the other exciton states that exist would all be at higher energy, all right? So, so why did we choose that? Well, for two reasons. One is it's very well studied in the literature, so we, can identify everything. And the other is we had it sitting around. We had both the doped and the undoped, and a good method for exfoliating it. But I would certainly not say it's unique or even the best choice for any of this.
Yeah. Currently the reports about the tungsten-based material, I think it's kind of oversimplified. Since we are working on some, look at the Bell monolayer, and after the spectrum, the Bell monolayer, and if you can encapsulate the sample with boron nitride, you can see much details of the spectrum. You can
You're
see
talking about like the fine structure of the excitons?
Excitons, biexcitons, or even charged biexitons. Some paper claim that, right?
Yeah, we've seen all that. Yeah, exactly. So that's why I say it's really nice, because all of that is identified in the literature. So we see all those lines and we can identify them.
Yeah. But if you put two layers together, you can see, you are increasing a lot of possibility, right?
Yes. Well, so again, so when we put two layers together, you get indirect transitions, but those are energetically far away because of the band offset, and they have much longer lifetime. So we're not worried about being confused by indirect transitions. The indirect transitions are very different, in a different spectral region and a very different lifetime characteristic. And the other thing, of course, we do a control with and without the metal layer. And so if there's something that appears in the bilayer that's just due to the fact that you have a bilayer, then you'll see that without the metal. And so comparing with and without the metal is a crucial test for all this.
Yeah. Okay. So it might be just maybe a suggestion. It might be to use like a molybdenum or molybdenum, some kind of simple structure in terms of optical spectroscopy.
Well, they're all variations. They're all, in the same family. The energy scales are different. For some of the materials, and actually I think that was another reason why we chose this, because it's right in the Thai sapphire emission range. But in general, yes, you could probably pick one. The one I would want to do next is one which had a much better binding energy. So the binding energy of the exciton is like 80 to 100 millivolts. And I think you can pick other materials that have several hundred. And so that, I think you maybe think it makes things simpler in that regard, just because the the energies are further separated from each other. But all of these, these lines, biexcitons, trions, indirect excitons, those are generic. It's not something unique to tungsten. It's just that it's been well studied in tungsten, so we know what all these lines are.
Can you go to the slides you show the spectroscopy there?
The first one?
The first one, yeah, you should Q, yeah. If you look this, the Q peak there, for me, it's like the same energy as the bi-exciton in the monolayer structure.
No, no, we know where the bi-exciton. So the exciton, this thing has been well established. So first of all, the power dependence of the bi-exciton is it's a telltale for the bi-exciton. So you can identify a bi-exciton because it goes as the square of pump power rather than just linear with pump power. And the other is that energetically, you know where it is in tungsten because the experiment's been done, and that's this experiment. Okay, so here's the bi-exciton. Okay, and that's way down here, sitting on top of the.
No. I don't think it's bi-exciton. Come on, this Tony Hans paper is the very early report for the bi-exciton, right? I mean.
Oh, so you think Tony Heinz is wrong?
Yeah. I think he's wrong. Yeah.
Okay.
Two years ago, there are few papers published on Nature.com after the encapsulated bone nitride and use bone nitride to encapsulate the monolayer. They can see the totally. I mean the polaroids with totally 2 below the exciton, which is like a 20 MeV below your exciton. But look at this peak, it's like kind of, I remember it's kind of 50 MeV below your exciton, right? You imagine that you
in our case,
from
well, I'd be interested if you have a reference. I'd be interested if you send that to me. If there's some update, reinterpretation of Tony Heinz's work. I mean, they did the intensity dependence. And found the square law. So my understanding is that they're properly interpreting that, but I am certainly interested if there's more recent experiments on that. Just a couple of points. One is that line isn't there. I mean, so this is the sample without the metal layer, and the Q line doesn't appear, okay? And the other is when we do the power dependence, the Q line scales linearly with the exciton. It's not going as the square of the exciton. So it's not fitting the expected power dependence for the bi-exciton. Certainly if the bi-exciton has an energy in that region, it would lead to more complications because you'd potentially have 2 lines in the same place. But I think you can still distinguish them by going to low power because the bi-exciton line simply goes away at low power. But I also have to say, Bondarev did the theory for the bi-exciton, like the same theory that does all this also is the theory for the bi-exciton, and he got it in agreement with Tony Heinz's result. So I'm a little surprised that that's being reinterpreted, but science moves on, so that's certainly possible.
Yeah. I mean, if you think about the bi-exciton, you have 4 particles, but from their paper, you have a binding energy of 50 MeV. Look at triangle, you have 3 particles, but the binding energy like 30 MeV. I don't think like a 4 particle system could have a much higher bonding energy or even high bonding energy than the 3 particles.
Oh, we're not saying it's a lot higher. We're saying it's comparable. But it appears at a different spectral position because the photon is the difference between the initial and the final energy. And so we're not saying it's a lot more bound, right? So if I go back to that theory, no, actually the theory I think is only in terms of photon emission energy. I don't know that I have the plot for the actual binding energy. The binding energies are comparable. So I'm not saying that the quaternion is more bound than tryon. I'm saying it's comparable in binding energy.
Okay.
But it comes out at a different spectral position.
Yeah, that's why I say there's a lot of possibilities here for this kind of material. For me.
Yes, and we have thought about those for a year very carefully, and we're pretty sure we've eliminated the possibilities. However, if you do have some recent work on bi-excitons, I would be interested in getting that.
Okay, thank you.
I see Manu has their hand raised.
Hi. Thanks for the nice talk. So just I have a simple question that, I mean, you mentioned about the doping being a critical things in this, right? So what exactly the optimum doping for, I mean, for this bilayer structures to observe this quaternions? I mean, is there
Yeah.
like some type of,
I don't have a number for you. I mean, there definitely will be an optimum because you know you want to put a lot of dopants up, but you don't want them to be so many that they form a Fermi level and start screening out your other effects. So you want to be sort of in the low density limit, but as high as possible in the low density limit without forming a Fermi level.
Okay. So, I mean, another point was actually you mentioned about the polaritonic kind of interactions in this quaternion. So, is it actually some kind of related to the light induced effects in the I mean the polaritonic, or like is it similar to the renormalization of this some kind of density of states that is related to the system that can introduce the superconductivity or something like that? Because what is the I mean significance of having a polaritonic I mean interactions for this? That's what.
Okay. Well, so the way that I think, you know, there's sort of two ways you can think about a polariton condensate. If I'm talking to AMO people, I say, imagine starting with a photon, which is a good boson, and then you turn up its interactions by mixing it with an exciton, and you get these really strongly interacting photons, okay? If I'm talking to semiconductor people, I say, imagine you start with an exciton, and then you turn its mass down by several orders of magnitude. You make it super, super light by mixing it with a photon. All right. I mean, and so both of those are true, right? I would say the main thing that happens, so you see there's this effective mass of the photon just from the cavity that persists when we, you know, so that this mass here is basically a vestige of the photon mass, which is the bare mass here, okay? And that is like 10 to the minus 4 electron masses. So that light mass, I think, is the main advantage of polaritons over just excitons by themselves. We've made very, very light particles. Now, like I said, anything that has an optical transition can make a polariton. And so since we have an optical transition for the quaternion, you can make trion polaritons, you can make biexciton polaritons, you can make I think, Timothy, you may have even done some of the theory for some of these, but you can make polariton. Yes, there was at one point people were really interested in Feshbach polaritons of sort of tuning near the biexciton resonance and seeing you know, something analogous to the Feshbach resonance.
Okay, thank you. I think
Are there any other hands raised?
Oh, I see. That little blue thing is a hand.
Yes, or if, actually, I don't know how to do that. So if you have a question and don't know how to raise the hand, maybe just speak out anyway.
Yeah.
I had a technical question about the image charges. So I've seen a few papers where they treat the image charge effect, that they write it as a series expansion. So it seems that at twice the distance of the image charge, there's an image of the image. And then at 3 times, there's an image of the image of the image. So is there some reason? I've also seen papers that don't account for that. So is there some reason why one is chosen and not the other?
I think it's a perturbative approach, right? Because, you know, the effect goes down as 1 over R, right? So the further away those are, the less contribution they're going to make. So I think one could write like an infinite series and then just truncate it and say the nearest ones are the ones that make the dominant contribution.
I see. Okay. And I don't suppose, did Bondrev think about what will be the effect of the next order?
No, I don't think so. Neither did Yudson. I think, if I remember right, it's like 3 times further away. It's not just twice as far away. It's some, odd. But, you know, I'm not sure I remember that right either. But in general, I've seen that kind of infinite series, and they just truncated like a perturbation series.
Mm-hmm. Okay, I think there are no more questions. So this is where we would thank David again. And okay, we have the microphones closed.
Yeah,
so I
they
do all the
they
clapping.
need to have like a little hand clapping icon or something like that, you know. Okay, well, it's been fun. And yeah, anybody who wants to email me with any comments, updates, I mean, it's both fun and also makes it hard when, you know, there's so much literature on this stuff that you have to go through. You know, you can miss things without realizing it sometimes. But it also is what makes it possible to think you know what's going on, because a lot of it has been studied.
Okay, so I see there is actually an applause button. So Dustin is applauding and Chiwa.
I don't even know how to get my button.
There's a button. There's a button. You can do that.
I don't even know where those buttons would be. Maybe I can't do it if I'm screen sharing. Okay, I'm going to stop. Yeah, stop screen sharing here. Okay, great. Okay, well, hopefully next time or sometime we'll see each other face to face, at least some subset.
I hope so too. And,
yeah.
Hopefully it'll be soon.
Yep. Okay, and we'll be in touch about perovskites too at some point. I think we were shut down in the lab, and apparently some lasers that were sitting non-used for several months, you know, like got dust in them, and so we have to like completely clean all the optics and get things up to speed again. So, okay, all right, we'll talk to you later then.
Thanks very much.
Thank you, David. Thank you.